qx subtract b transpose x for x in Rn. Okay. This is our setting. And Q is an SPD matrix. Okay, so Q is SPD. So symmetric, positive, definite. Okay, so Q is SPD. And our gradient descent algorithm then which is x k plus 1 equals xk. So this is k theory. This is next iterate. Subtract alpha k times the subtract alpha k times the gradient of f at the kth iteration. Okay. So then this algorithm for k equals 0, 1, given this initial guess, converges, okay, to the unique local minimizer. So if it's a unique local minimizer, it's a global minimizer. Because we only have one local minimizer or convex function, then it is the global minimizer. So the unique local minimizer x star equals Q inverse B. For x R and B, B is in R and B as well. Let's add this. Okay. So, and if, so there's a if. So if alpha k, I forgot if it's 2 or 1, but it should be 2. So 2 divided by the maximum eigenvalue of Q. So lambda max Q equals max, let's use x. So x is in Rn and x is not 0 vector. This is x transpose qx divided by x transpose x. So using the inner product notation, this is also q times x, then inner product with x itself and divided by, so x transpose times x is x mod squared. All right. So this is a theorem, and we have a rate of convergence. So remember, we have a rate of convergence, and the rate of convergence is given by x k plus 1 to iterate, subtract our optimizer is less than or equal to rho of alpha k. So we'll define this in a moment. We defined it last time. Let me this. So. Okay. So where this rho, so this guy, rho of k, rho of alpha k, is our rate of convergence, and it is a maximum among two numbers. So the first number is 1 subtract alpha k lambda minimum q. And 1 subtract alpha k lambda maximum q is the rate of convergence. All right, so last week, we were in the middle of proving the theorem. So heuristically, we'll explain what heuristically this theorem tells us. Okay, it tells us in order that our gradient descent algorithm converges, the step size has to be small enough. So the proof we did was using the error equation. So here I'll briefly recap how we derived error equation. So we start actually from so we actually start from the gradient descent algorithm. We subtract the local minimizer on both sides. But then we take advantages of, we add an artificial term because x star is our local minimizer. The gradient is 0, so we can add this term. Okay. So then we exploit that. So then we apply the Taylor expansion on x star, and we make use of the Hessian of f is exactly q. Okay. So we use this formula, that is, so let's say this is g of x is x transpose ax, the Hessian, the gradient of g is a plus a transpose x, and the Hessian of g is just a plus a transpose. Okay, so if q is symmetric, it means q transpose is q itself. So and then we take advantage of this. Okay, we take advantage of this. We use Taylor expansion on this, and then we obtain the error formula. Okay, this equals. So this is identity subtract alpha k q square times xk subtract x star and inner product with xk subtract x star. Right. Okay. Then we take advantage, actually we use the definition. So this thing literally less than. So this is Cauchy-Schwarz inequality. So Cauchy-Schwarz inequality says this is less than maximum of, I forgot the letter I used, but let me use the Greek letter Kasi. So now we use Cauchy-Schwarz inequality. So think about this. This number is the maximum possible this thing ever achieved divided by. So think about this, okay? So normally if we read a research paper, even this step won't be written explicitly. So from here, people will directly give, oh, this is bounded by the max, so this is like a given. But once we read those research papers, we need to know each sub-step, how they break. So for example, so from, okay, so from how does one, I didn't bring any notes, but okay, think about without this one term, okay? I mean, if K theory is X star, then we're done, you know? So without this term, we'll look at this term, okay? So how to from here, so if we read a research paper in any machine learning, so it will be directly from this step to this step, okay? How does it? It's true, is first we multiply and divide this, okay? And then we combine these two, okay? This guy divided by this. Of course, this is less than or equal to this. Because, you know, this is the maximum possible, whatever this type of quantity end up achieve, okay? This is just one type of quantity with this as the input, but this is any cascading on n. So of course, this is less than that. And this is by the definition, the maximum eigenvalue, okay? Not by definition, but I mean, we can show it, and so I chose to omit, but it's in the lecture notes. So it's using eigen decomposition. Okay, so now we're here. So here is so this applies. So we convert it. Like how fast our gradient descent algorithm will converge to an analysis problem, or say a linear algebra analysis problem that we want to analyze what is the eigenvalue of this guy. Okay. All right. So, and then we use eigenvalue of polynomials of a matrix is equal to polynomials of eigenvalues of A. So P is a polynomial. Then we use this, and this guy becomes what? Becomes the maximum possible. So it becomes the maximum possible of 1. So identity matrix becomes 1. Okay. So 1 subtract alpha k lambda q. now next is for the fixed alpha k. So for a fixed, right now we fix our step size. This quantity, so this quantity right here. Okay. Oh, sorry, I forgot a square. My bad. Okay. So now, for this quantity right here, okay, its maximum value, so this is 1 subtract, so basically we have this 1 subtract alpha lambda, this function, okay? So if we fix alpha, it's a function of lambda. This function achieves its maximum because if we fix alpha, okay, this function looks like what? This function looks like this. I mean, calculus 1, okay? So we plot this function. The graph will look like this. So now if we have an interval of lambda, so for example, if this is our interval of lambda, and we know that lambda minimum is greater than 0, lambda max is somewhere more positive. So the maximum value of this guy is sure achieved at either one of these two ends. Okay, so the max of this function, okay, for fixed alpha is achieved either at lambda min or lambda max. Okay.
What are the two lines above the max of?
Oh, you mean here?
No, sorry. Over the two, like.
Oh, here?
Yeah.
Equal. Yeah, it's equal.
Oh.
So.
So,
and this is the reason why.
Equal to what?
This equality equals maximum. So this is the maximum of like lambda cube, okay? So we change this lambda. We have, for example, if A is an m by m matrix, real symmetric, it has n real eigenvalues, okay? Positive definite. So then what happens is we take the maximum value among these n eigenvalues. So, for example, if this is lambda, this lambda is in the set of eigenvalues of Q. So well, this notation is better. I don't know which one is better, but this quantity achieves its maximum at the two endpoints. So either the maximum is the minimum eigenvalue of Q, or 1 subtract alpha k lambda maximum eigenvalue of Q. Okay. And this thing is multiplied with x k iterate subtract x dot square. So last time we were here. Go ahead.
I just want to clarify that in your theorem, you don't have the squares in that maximum set, but in over there you do.
Yeah.
Okay. Why?
There is no square here.
Oh, okay. Great. Thank you.
So last time we were there. So once we figured out this, to guarantee convergence, we need every time our error shrinks. So this is our error. Okay? So this is the error at the next iteration. So it's how far we are from the local minimizer, so our optimal point. And this is the error of our current iterate, or say previous iteration. So we want the error shrinks, which means for convergence, okay, what we need is that quantity right here is less than, so is less than 1. So we choose convergence. We choose alpha k such that. And I do want to clarify why we want to keep this alpha subscript k here, because in next class when we analyze the steepest descent, which is line search, so we'll see that this alpha k changes every time. Okay. But right now, alpha k, so we want to choose a fixed value of alpha k, okay, for all k, such that this quantity right here, that is the maximum of those two values. Is strictly less than 1. Okay. Strictly less than 1 means it's a sufficient condition for our algorithm to converge, because each time our error will shrink. So that, for example, so when we have the cumulative effect of running multiple iteration, then eventually, it's like a geometric series with ratio that is less than 1. Eventually, we multiply enough, we get 0. Now we let our iteration number go to infinity. Okay, so we get 0. So now we analyze this. The analysis is very similar. Okay, the analysis is very similar to this graph. So now we know, once we know that this is achieved on the boundary, now we consider, okay, so we consider two functions. We consider two functions, that is g1 of alpha. So now we consider this as a function of alpha. So the first function is 1 subtract alpha lambda min. So lambda min is just a lambda min of q. Okay, so I'm saving some space. All right. The other is g2 is alpha equals 1 subtract alpha lambda max. Okay. So think about this. Lambda max. So let's plot the figures of these two functions. Okay. So now our horizontal axis is alpha, vertical axis is g. Okay. So this is an absolute value function of alpha, but inside it's a linear function for fixed lambda minimum. Okay. So if we write it down, explicitly, it is 1 subtract alpha lambda min if this is greater than 0. If it's greater than 0, greater than or equal to 0, it means, so if this is greater than or equal to, but if we solve in terms of alpha, it's going to be alpha is greater than or equal to 1 over lambda. So, and it is alpha times lambda min subtract 1 this is alpha is less than or equal to. And this is alpha is greater than 1 over lambda. Okay? So where is 1 over lambda min? So we may set it here. Okay, so 1 over lambda min. And when alpha is less than that, this is a linear function of alpha with a negative slope. So lambda min is positive. Okay, so SPD matrix, and we have lambda max is greater than or equal to lambda min is strictly greater than 0. Okay. So actually this case applies to lambda max equals lambda min, but that normally won't be the case, because if that's the case, our algorithm will converge in one step. But this proof is actually okay for that. Okay. So now we plot the first function. Okay. So before alpha reaches this 1 over lambda min, it's a line with negative slope. So slope is minus lambda min. Okay. And after that, it is alpha times lambda min, subtract 1. So lambda min is positive. So now, after this, this is a line with positive slope. So it's basically a piecewise linear function. Okay. So this is G1 alpha. So now let's look at G2 alpha. G2 alpha is exactly the same. I mean, the shape, I'll say, the type of graph for G2 alpha is exactly the same as G1 alpha, except the cut point is now 1 over lambda max. Okay, so lambda max is greater than or equal to lambda min, so 1 over lambda max is somewhere here. All right. Okay. So, and we can do the same thing. We can do the same thing. We can do the same analysis as above. So what we will obtain is, before alpha reaches 1 over lambda max, it will be a line with a negative slope, lambda max. So, but lambda max itself is bigger than lambda min. So the slope of this line should be steeper. Okay. So which we will obtain these two lines. Okay. So what we want to do is, so this is G2 alpha. We want to choose an alpha such that, so we want to choose alpha as small as possible such that the maximum of these two, okay, is less than 1. All right. So when alpha is 0, we can see these two lines like intersect one another. So when alpha is 0, both of them is 1, right? So when alpha is 0, so this is alpha is 0, both of them is 1. Okay. So we have something like that. All right. Okay. So now we choose alpha from the graph. Okay. So now we choose alpha by reading the graph. Okay. So we choose alpha bigger. So if we choose alpha here, I mean, this line literally goes way above. Okay, so if we choose alpha here, so if we choose alpha here, both G1 alpha and G2 alpha will be greater than 1. So, but when we move our alpha, when we hit this point, where is this? This is actually, by symmetry, this is 2 divided by lambda min. So once alpha is less than 2 divided by lambda min, this quantity will be less than 1, okay? We reach, we move. But this quantity, G2 alpha, is still greater than 1. And once we move past this point, okay, by symmetry, this is 2 divided by lambda max. So basically, if we solve, so by the graph, so we need to solve. So we solve for alpha in G2 alpha is strictly less than 1, or 1 minus alpha times lambda max is strictly greater than 1. And and this is when, so this is when. So when alpha is greater than 1 over lambda max, this becomes alpha lambda max subtract 1 is less than 1. So alpha is less than 2 divided by lambda max. Okay. And we observe that if we move past this line, okay, so if we move past this line, both quantity, G1 alpha and G2 alpha, will be less than 1. So once we move past this, so it means a sufficient condition is to restrict alpha is less than 2 divided by the maximum eigenvalue of Q. Okay, so this implies this implies what? This implies we have to choose our alpha is between this value for convergence. Okay. Excuse me. Okay, now let's learn. Now let's learn when it is the optimal alpha. What is the optimal alpha to choose in the gradient descent scenario that we want our algorithm converges to our optimal fastest? Okay. So keep in mind, we want to keep in mind our fastest rate of convergence is we choose the alpha so that this quantity is minimum. Okay. So fastest rate of convergence. Yeah, this pen. So the fastest rate of convergence is we choose alpha such that this quantity is the smallest. Okay. So this is our rho alpha k square defined earlier. Okay. Okay. So fastest rate of convergence is we choose alpha k such that rho alpha k is the smallest. Okay. So now we return to this graph. Okay. We return to this graph, we examine this range. Which point of alpha will give us the fastest decay rate? Think about this. If we choose alpha too small, it's kind of a bad thing because it won't converge, so every time we move too little. But we don't want to choose alpha too big because we may encounter the case that, so well here, we choose alpha too big, we get here, we want to get here, okay? So now let's look at the diagram. It is the minimum possible of the two quantity, okay? So this quantity goes up, which is, G1 alpha for lambda min, and G2 alpha goes down, but then go up, okay, then goes up. So this point right here, okay, is the minimum possible because we move here, okay? This goes up, this goes down. So right here, like the maximum of the two. So now let me draw the maximum. So the maximum. So if we draw the graph of maximum of the two. So if we draw the graph of the maximum of the two function, it is this line. So before this point, this is a maximum. After this point, this is a maximum. So the maximum of the two depend, like with alpha being a variable, is this line and this line. Okay, so it reaches its minimum here. And that is when those two quantities equal to one another. So this is our alpha star. So if we choose alpha k such that the maximum, so this one equals maximum of G1 alpha k and G2 alpha k is the smallest, then it is when G1 is G2. So this implies G1 alpha k equal to G2 alpha k, i.e. it is 1 subtract alpha lambda max equal to 1 alpha k times 1 subtract alpha k times lambda min. So this implies, so we're here, right? So we're here, alpha is already less than lambda min, but it's greater than 1 over lambda max. So what happens is alpha k is greater than 1 over lambda max, so this, the left function will be alpha k times lambda max subtract 1, and the right function, because alpha k is already on the left of 1 over lambda min, so it is alpha k times lambda min subtract 1. And now we solve for alpha k. Sorry. This is 1 subtract alpha k times lambda min. So now we solve for alpha k. And if we solve for alpha k, we find, so the optimal step is lambda k equals 2 divided by lambda max plus lambda min. So this is our optimal step 7.
Wait, you mean
Sorry, alpha k. Alpha k.
Okay.
My bad. This is alpha k. Yeah. Sorry. So this is our optimal step size. So the fastest, this is the optimal step size, which means our gradient descent algorithm will converge fastest to the local minimizer. And what is the rate of convergence? Okay, so the rate of convergence is we plug in this alpha k here, we evaluate these two. We can evaluate either one because they are equal. Okay, so when the fastest is achieved, they are equal. So we evaluate either one. So this rho alpha k square. So yeah, we can, without the square, we only evaluate this absolute value. So equals 1 subtract alpha k lambda min equals 1 subtract alpha k lambda max. Okay, when alpha k equals 2 divided by lambda min plus lambda max. So we evaluate this one, we evaluate the first one. This is 1 subtract 2 over lambda max plus lambda min times lambda min. Okay. So the 1 is basically, we just use common factor. Okay. This is 2 times lambda min, and then this is 1, so it's lambda max plus lambda min divided by itself, and it's lambda max plus lambda min, subtract 2 copies of lambda min, so this is absolute value of lambda max subtract lambda min divided by lambda max plus lambda min. Okay. And because lambda max is greater than or equal to lambda min, and every eigenvalue of Q is positive, so this whole thing, we can remove the absolute value. And we want to divide, we do want to divide lambda max, we do want to divide lambda min to the bottom. So we have lambda max divided by lambda min, subtract 1. And this is lambda max divided by lambda min plus 1. And we have a name for the lambda max divided by lambda min. This is called the condition number. This is called the condition number of Q. Actually, it's also the condition number. So where kappa is defined as the maximum eigenvalue of the Q divided by the minimum eigenvalue of Q is called the condition number. So if you have played with optimization algorithm before, watch any YouTube video on, for example, a research seminar, so this word is often popped up. It gauges the difficulty of an optimization problem. So it's a condition number of the SPD matrix. Q. Okay. All right. So if the condition number is big, our algorithm will converge very slowly. Think about it. Okay. So this is a rate of convergence. So this is our rho. This is our best rate of convergence. So is the best rate of convergence for the gradient descent algorithm. All right. So if we rewrite the theorem, So when alpha k equals 2 divided by lambda max plus lambda min, then what we have is our gradient descent algorithm will converge at a rate of that one. So rho alpha star where rho of alpha star is this. So at the second half of the semester, when we introduce, after we learn conjugate gradient, we'll learn an innovative approach introduced by Nesterov maybe 20 years ago, which is a foundation of current machine learning. So if you have heard of a method called ATOM, the M is momentum. Okay, so once momentum is introduced, this rate of convergence will be improved drastically to square root of kappa k subtract 1, square root of kappa k plus 1. So this is like magnitude faster than this one. So think about this is approximately equal to 1. So I don't want to write it here. Okay, so I just want to make a remark, okay, to motivate why we want to introduce momentum, which is most widely used machine learning optimization algorithm, which is called ATOM. So this will approximately equal to 1 when kappa is large. Okay. Then kappa, which is a condition number. So for problem defined on graph, so we may go a little bit off topic, but kappa is big O of n, and n is, if we are solving an optimization, for example, if the Q is a graph Laplacian plus an identity matrix, n is the number of nodes in the graph. Okay. I just want to say this could be large. Okay. So kappa could be large, and gradient descent algorithm will be extremely slow without modifying certain components of it, and it will become the motivation of several consequent algorithms we learn. So for next time we will analyze what is called steepest descent. Okay, so then next we'll learn CG, which is conjugate gradient. For conjugate gradient, we have to explore the information from Hessian, or at least when we prove we have to use that. So the next we use quasi-Newton. So this is like a So every next fancier method is motivated by the drawback of previous method. Okay, so so this is our canvas. So this is our canvas. So this is our canvas. Okay, so if we go to coding lectures, we download this notebook. So it has a file name of IPYMB, and it's basically a Jupyter notebook, a Jupyter notebook, if you'd like to name it. And then we go to Colab. Okay, so this is Colab. So Colab is something by Google. Okay. Yeah, maybe I shouldn't use the darker theme. So let me use the light theme. Okay. So this is Colab. Colab, so it's website. So you can just Google Colab Google. There we go. The first link is Colab. And what we do is we can simply open Notebook and then go to upload. Okay, so then we open the Notebook we just downloaded. I mean, there are plenty of how to use Colab instructions on YouTube. So for example, you can Google Colab 101 on YouTube, and you get much better instructions than my babbling here, you know. So, but here I just want to introduce us to the tool, Colab. So in the first coding lecture, we'll learn. So I assume everyone has used MATLAB. Okay. So NumPy, which is the equivalent of linear algebra. Why it's not? Why the? This is okay. So it's not. So the projector is not full screen. That's very annoying. Okay, here we go. All right. So what happens is Colab is perhaps our cheapest way to use an advanced GPU that has a decent floating point operations per second and a decent double precision computational power. So how do we use GPU is we click Edit in the notebook setting, okay? So we can choose CPU. So it uses, actually Colab uses the Xeon CPU that is better. So for example, it has ECC, which is called the error correction, you know, in our memory. That is much better than our consumer CPU, you know. So for example, if we choose Tesla T4 GPU, okay, we can even choose this if you pay money. So for example, if your advisor has money, you can ask him or her to, you know, to buy you a Colab Pro. And it's extremely fast, can train more than large language models and blah, blah, blah. So, and you can even use CPU if you know how to play with the syntax. So here we use T4 GPU, okay? Then what happens is, if we want to start a notebook, we simply click this connect, okay? So then, if I'm lucky, so Google will tell me, oh, it's connected, okay? So it tells you, oh, you have 12 gigabytes of RAM, and you have GPU RAM, which is like dynamically, unfortunately, it's dynamically allocated because it's a free account. So, and this is basically Colab. So and this is called a cell, okay? So this is called a cell. Yeah, let me make my mouse bigger. Wow, this is Windows 11, and it's kind of bad. Okay.
I agree.
How do I make my mouse bigger? Now I can't find it. Maybe I should search it. Okay. Okay, here we go. Yeah, size. Let's use this. Oh, even this. Let's make my mouse bigger. Okay, that's much better. Okay, so that's too big. Okay, this is kind of good. So this right thing right here is called a cell. So hopefully the font size is okay for everyone as well. So Okay, so this thing is called a cell. Whenever we double click a cell, it's entering edit mode. So we can double click. Okay, so we can see it's entering edit mode. We can edit this. So for example, we can add something here. So the double pound sign means it's a section. Okay, so for example, hello. And then we hit Control and Enter, or Alt and Enter. You know, oh, this actually uses a different, so when we hit Shift and Enter, it will render this cell. So for example, if we hit Shift and Enter, boom, it's back to this. Okay. So we can type LaTeX, like I said here. Okay. And we can type code by using this apostrophe, this triple apostrophe sign. But there are plenty of instructions online how to use Colab. So then this is called a code cell. Okay, so this is called a code cell. So when we hover our mouse on a code cell, you'll see a little play button right here. This is run this code. Okay. So this we hit Control and Enter, and it print these messages. So this is the print is perhaps the most handy, one of the most handy things. So by the way, this notebook is available on Canvas, and I will upload the annotated one, which will learn a few more coding things. Okay. So different from MATLAB, everything is preloaded from path. So for Python, if we want to load a module, so for example, in MATLAB, everything is preloaded if you put it in the path. That's actually an inefficient way of looking for names because it occupies a huge chunk of memory, okay? So then for Python is we import these modules as needed. For example, we can import NumPy as NP. So this is like tradition. You can actually import it as import NumPy as NumPy, you know. So something like that. It's even okay. So, but NP is tradition. So, okay. All right. Oh, it has only even IntelliSense auto-completion. So Google is learning from Microsoft. Okay. So then this is PyTorch. So this is PyTorch. Okay. So this package right here is PyTorch. And so here are some introductions. And also, this is my recommendation. So if you're rich enough to build a workstation by yourself, so this is my recommendation. If you wanna do some serious machine learning, so I recommend to build a desktop, not laptop. You know, so laptop is bad. So laptop is not recommended for machine learning. If you want to use laptop, just use Colab. Okay. So I recommend build a desktop around this GPU. Okay. So if you're serious about deep learning and you have some spare money, I recommend these two GPUs, which is 3090 or 4090. And 3090 is especially a bang for your buck. Okay. So if you can find one, but this one is discontinued, I believe. For example, right now we are already in the 2.0 version. Oh, it's 2.01. Okay, so it's good. And this CU here means CUDA, which means we're on GPU. Okay, so CUDA, the newest version, I believe is already 12, but this is backward compatible for 11. So it's just CUDA is something like a C code on GPU. Okay. And if GPU is available when we run this line, it will return true. Okay, so GPU is available. So when GPU is not available, for example, if we change this to, so if we change this to CPU, which we'll do in the next, so we'll stop and save. So we're back to CPU. Okay, so connected, right? So we have to run everything back again. For example, we run this one. Okay, so it's down, and then we run this again. There won't be CU anymore. Oh, it's still CU. Okay, I guess, but this will be false. Okay. And this one, if we have an exclamation mark in front, this will be a command line prompt. Okay. So for example, if we run this, we will see something we typed in the terminal. This one will give us the CPU with GPU information, but right now, if we run this, we don't get anything. So command not done. But if we're back to GPU, okay. So if we're back to GPU, okay. So now we run this command again. We'll get our GPU information. For example, this is Tesla T4. Where is it? Oh, right here. Okay, so it's a Tesla T4, and it has this much of memory. It has, actually it has 16 gigabyte of memory, and it has 70 watt computing power at our disposal. So it's better than I expected. But this is dynamically changing, so this some caveat. Okay. I mean, once we imported these two key packages, we can perform like our computation. Okay, so I'll skip this. So this is a good habit of setting the seed. For example, we can set manual seed. And if you're on GPU, you may want to do this. Okay. And for example, we can check. This is NumPy version, but we already checked it. Okay. So for example, once we imported NumPy, we can have these arrays. So this is essentially a matrix. Think about it. Oops. Okay. What is this? So this is the 3-row by 2-column matrix, right?
Yes.
So if we run this, we will see this is like a matrix right here. Okay. So we use the bracket to make things like handy. So unlike MATLAB, if we use MATLAB, we know that if we want to like separate a row, we use these semicolon. Okay. So in Python, so if we want to create a matrix, the syntax is always we use these brackets, and the separator is always comma. Okay, so in MATLAB, we use semicolon. But in Python, the syntax is slightly different. It's more consistent. And so this is NumPy way. And if we have PyTorch, then PyTorch, everything in PyTorch is called tensor. So we can create the same thing in PyTorch. Okay. So for example, so actually this is a help, you know. So this is a help of this function. But right now we don't have to know it. So if we run this line of code, we hit Control and Enter, and it gives us the same thing right here. So almost the same, but this one is a float. So for example, if we add print, we can add something like this. Okay. So for example, this without specifying the type, NumPy will allocate the type of the variable based on the thing you input. This is called dynamical typing, but if you put a 10.0 here, it will become a float. Okay. But without here, get back to the integer type of matrix. And if you check this type, so PyTorch will by default allocate float as your default. So it has several, for example, handy command. For example, this is NP array, and range 10 is basically from, so this is from 0 to 10, non-inclusive of the right end. I have this effect. I forgot how I enabled it, but yeah. Okay. So for example, if we print x, we'll find this is 0 to 9. Okay. So we can sum it. For example, x is this, vector. So if we sum it, it's a sum from 0 to 9. Okay. So we already run this. Let's and another way of summing up is this, because x. Okay. So x is an object. We can check. So Python have. So you don't have to write it down. Okay. So it's kind of writing down is inefficient of attending a coding lecture. So just listen to me babbling. Okay, so you can figure out by watching YouTube or like playing with the notebook. But writing it down kind of like waste of precious time. Listen to me. Watching the screen. Okay, watch the screen. What happens? So for example, this dir of x, it gives us what method we can apply on this variable. So we hit Control and Enter. We'll find we have this function we can apply on this variable. There are lots of variables. Okay. So for example, run, sort, okay, like sum. And if we see this double underscore, it means it's a built-in method for Python. For example, we can even redefine this method. It changes the behavior, for example, how we add to tensors, vectors, whatever. So my point is these are changeable as well. Wow. Okay. And even you don't know, you can always ask ChatGPT, So I find it's a very handy like helper for me. So even I've coded for 20 years, I still. So you can do this. Okay. So when you, for example, actually, so when you do x dot, Colab will auto-complete the command you want. For example, you can find you have this many methods to choose. Okay. So if you see, I'm not sure, but this is following VS Code's. This color code, so Visual Studio Code or VS Code is an editor from Microsoft. And if you see this purple cube, okay, this is the function. If you see, so this will be like a function, but if you see this type of,
cube,
this is a like built-in function. If you see this will return. So this will return. For example, this will return some descriptor. Okay, but these are some handy tools. For example, you can do sum. Okay, so like built-in functional method, you click it, then it auto completes the parentheses for you. It doesn't? Oh my god. No. So VS Code will, but okay. So if you type one bracket, it auto completes another bracket for you. So we can use this as well. So let me. So basically, if we run through this list, okay, so we can get an idea of what thing we can do. Okay. So for example, right now this x. What is x? So x is a NumPy array, right? Okay. So this is the NumPy array, and we can convert it to torch. Can we do that? I'm not sure. Maybe we can in 2.0, but normally it's from NumPy. Okay, you can. Okay, and we can convert it back to NumPy, for example. And this is a famous ReLU function. So right now, x is, So right now, for example, if we check the type of X is a torch tensor, oh, it's back to NumPy? Okay, never mind. So let's do it here. Okay. So it's now a torch tensor. So then we can use this clip method, for example. So, okay. So if we want everything that's less than 5 to be 0, we can use this click function. So if we click, sorry, to be 5. Okay. So for example, the ReLU is everything less, this is a ReLU function, if it's 0. Okay. And, but everything is positive, so, so for example, this we can do NumPy as well. Yeah, unfortunately I don't have time to go through everything. Let's continue next time. Let's stop here. Yeah, let's continue. Let's continue.
I sent her.
Thank you for the note. It helped me a lot. Like I am studying, and your note is so clean. My note is so junk. Nih aku dan tuh last step mau
ভিডিওটা আমার লাগবে না ভুলে ভিডিওটা আমার লাগবে সব ভিডিও